All right. So continuing our look into current carrying wires, we're going to now look at the forces exerted on conductors in a magnetic field. So remember that we said that magnetic fields exert forces on moving charges. And if a current carrying wire is just a source of moving charges, of course, it must experience a magnetic force. So you can sort of dress up the QV cross B force into IL cross B for a wire, but I find it much more easy to remember if we call this the BIL force, where this L is the length of the conductor perpendicular to the field. Because remember, in our QV cross B, it's our right-hand rule, and you need to have some sort of perpendicular velocity. So this IL sort of encodes perpendicular motion to the. So first we'll sort of verify this, and we'll do more of an intuition-based proof. There's a much more involved proof using drift velocity, but remember that the magnitude of the magnetic force is given by QV perpendicular times B. Now, if you wanted the full force, you could, of course, do this with cross products. But now, we don't have just a single Q. We have lots and lots of Qs. So, in this case, we're going to say it's equal to Q total times their velocity perpendicular times the B field. And notice that we can actually expand out what this V term is. Because velocity is distance over time, and we assume that there's so many charge carriers that this drift velocity becomes constant. So this would be sort of the change in length they go perpendicular to the field divided by the time it takes times B. Now we can see where it's going because we get charge divided by time times our perpendicular length times B. And of course, this is just Q over T, which is a current. So we can write this as I times our perpendicular length in that segment of wire times B. So if we take this over the whole wire, we just sum up all the little delta L's and we would get our BIL force. FB equal to BIL. And this was more of an intuition-based proof. Like, it was not supposed to necessarily be the most rigorous thing in the world, but just to understand that BIL, the BIL, is a natural extension of QVB. Because if you expand your V into a distance over time, we can do some clever grouping and sort of make our velocity turn into a sort of current by associating that division by delta T with a different. All right, so to actually get the direction, it's just same old right-hand rule, because current is the direction of positive charge flow. Remember, conventional current. So here we have our current goes to the right. Our B field is out of the screen, so it points at me. So notice that means my palm is going to point down. This would be down. My current is actually coming at me, and my field points to the left. Again, down. My current points down. My field points into the screen. My force is going to be to the right. So again, what right-hand rule am I using? We're just saying that your thumb is going to represent the direction of positive charge flow. Only use your right hand for wires because current is always positive charge. And then your fingers point in the direction of field, right? Many fingers for many field lines. And then as a result, your palm is going to slap the charge carriers in the direction of the. All right, this is quite a little tricky ranking task we have here. So we have a current carrying wire. So there's a wire that lives in the XY plane like this. So it's carrying current at a very specific angle. And we're going to be interested in the force in different cases where we move the magnetic field in different directions. So we can either put a B field in the X, which is case 1, we can put the B in the Y, or we can put the B in Z, and we're going to rank the force on this wire segment in each of the cases. All right, so it's usually better to at least start with the justification, because we know that the magnitude of the force experienced is going to be B, which is the same for everybody in each case, because it says we're using a same B field magnitude, we're just changing its direction. I, which is the same in each case, it's I, and then times L perpendicular. So that must be where the change is. So we're really just looking at L perpendicular. So the more perpendicular the wire is to your field, the more force you experience. So first of all, notice that this wire lives in the XY plane. So what the B field does is it ignores any of your wire that's in the direction parallel to B. So we actually know that that means that F3, the Z direction B field, is going to exert the greatest force, because I have absolutely zero wire in the Z direction, right? I have some of it in the Y, some of it in the X, but I have no wire segment in the Z. So it feels the full force. So actually you get the full BIL. You get the full power of BIL in the Z direction. So now we have to compare X and Y. So this is why the angle was actually important. So we'll need this for the future, that this is going to be L cosine 30 degrees, and this is L sine 30 degrees. But the fact that the angle is less than 45 tells you that this wire is more flat than vertical. So what that means is that there's more wire in the X than the Y. And if you know your unit circle and work this out, this would be root 3 over 2 times L, and this would be 1/2 times L. And again, square root 3 is bigger than 1, so that means that this is the larger length. So this means that you would get more force if you put the B field in the Y, because that would mean that the force would act on the larger of the two components. So F2 goes in the middle, and F1 goes on the end. So why is this the case? Well, we're really just ranking. We're ranking L perpendicular. So the perpendicular length in this case would be only the Y direction, which is 1/2. The perpendicular length in this direction would be the X, which is root 3 over 2. And the greatest would be 1. So this is quite tricky. Now, qualitatively means that we don't really want to use the actual trig function components here. We just need to say, well, since my angle is less than 45 degrees, the length in the X is bigger than the length in the Y. So that means that you're going to want to put your field in the Y to get a larger force than the X, because you're going to ignore the small length. Magnetic force depends on current perpendicular, so the wire carries more current in the X direction. So if you ignore the X, you're ignoring more of the wire. Very tricky. Now this is not tricky because we already did all the work. All right, force magnitudes 1, 2, and 3. All right, so F1, we know that it's BIL. And in this case, we're going to ignore any length in the X direction. So this would be BIL in the Y and Z direction. Of course, there's no length in the Z direction, so we just want the length of the wire in the Y direction, which is 1/2 L. So this would be BI 1/2 L, or half a BIL of force. Same idea down here, except it's just the other component. Our magnitude is BIL perpendicular. And in this case, we ignore the length in the Y direction. So we do BIL that are in the X or Z directions. And in this case, that would just be the length in the X direction, which was root 3 over 2 times L. So we get root 3 over 2 of a BIL. And again, that is greater, right? Because we have a numerator of 1 here and a numerator of square root 3 here. And square root 3 is bigger than 1. And then for F3, F3 would be the same idea. Except now we ignore the length in the Z direction. Well, that really means we're ignoring nothing. Because if we want the length of the wire in the XY direction, meaning the XY plane, well, that's the full length. So we get BI times just a full L, because there's nothing that gets ignored. So we get 1 BIL. And that is the greatest. It does go from least to greatest here, because 1/2, that's about 0.5. That is 0.5. Root 3 over 2, bigger than 0.5, but it's less than 1. Because again, square root 3 is definitely not 2, so it's less than 1. And then 1 is bigger than both of those. All right, what if we wanted the wire to experience 0 force? How could we orient our field? Well, we know the whole trick is L perpendicular. So we know that if it is still a non-zero field and a non-zero current, we know that FB is BIL perpendicular. So FB equals 0 when L perpendicular equals 0. And how can you get L perpendicular equal to 0? Well, that means you need your wire to not be perpendicular to the field at all, meaning it's parallel. So that means B is parallel to the wire. We'll say direction of current. So that's what we want. Because if it's parallel, again, remember, if you tried to like do the right-hand rule, when we had like a QV, let's say I'm going to the right, charge to the right, B field to the right, you can't move your hand like that. There is no force. It's that nature of it being a cross product. Maybe we'll clean up my parallel symbol. That is parallel to the direction of current, or anti-parallel. So we want something like this, where this was your wire carrying current. We would want to orient our B field so that they're exactly parallel. All right, so now we'll do an example with our BIL force. Oh, that's interesting. Did I miss a question? Oh, no, I didn't. I just can't count. Like, why are we on 4 already? I forgot the right-hand rule was so quick. Rectangular loop. I give us the length and the width. It carries a clockwise current of 3 amps. So let's carry that all the way around. And there's a B field, constant, uniform magnitude, 0.1 Tesla out of the plane. We want the magnetic force on each side of the loop, and we'll draw it. All right, so this is not a case where we have to deal with the perpendicular, because notice that our wire is in the XY plane at all times, and our B field is in the Z. So we just get to BIL everything. So first of all, let's get the directions of everybody. So I'm just going to go clockwise. All right, so top, QV, QV, cross B comes at me, so this is going to be down. Then we have QB cross B, QV cross B goes left. Then we have QV cross B up. And then we have QV cross B is to the right. So interesting, we get this sort of like compression idea where the B field is actually trying to squeeze the loop. So what are the actual magnitudes now? Well, we can do that pretty easily, because we know that by symmetry, the force on the top is going to equal the force on the bottom. And that's going to be BIL. But what length do we use? Well, it says length is L, that's 2 meters, and the width is 4 meters down there. So BIW, which is B times I, which is 3, 4, so we get 12, and then the 0.1 makes that 1.2 newtons. So 1.2 newtons up and down on the top and bottom sides of the loop. Interesting. Got some nice symmetry there. Cancel, cancel. All right, same idea here. Got our shameless copy paste of the day, except just a couple minor changes. We have F on the left side of the loop is going to equal F on the right side of the loop. And that's going to be BIL this time. So we use our length of the loop, which was the other sides of the rectangles, which was only 2 meters instead of 4. This is a giant wire loop, by the way. And those also balance. So it's not the same force all the way around, but we see that there's pairs that are canceling. Describe the net translational motion of the loop. So this means the actual like moving up, down, left, right. Like, will it be changing where its center of mass is located? No. There's no net force. Like, so it's not going to translate, right? There are forces. There's 4 forces on this loop, but there's no net force. So it's just going to stay there. What about the rotation of the loop? Well, this isn't going to spin. Think about pushing down, left, up, and right on this rectangle. You're really trying to squeeze it. That's not going to rotate it, though. So there's no net torque on the loop, so you don't get any rotation. Alrighty? Now we have a very similar looking example where we have a square loop, but the B field is sort of changed orientation. So we can kind of look what's going on here. So counterclockwise current this time, very scary, the current direction. Let's find our forces. So it looks like our answers are going to be some variant of BIS, because our BIL, we have our BIL force, except L is. All right, so each side of the loop, and we'll label the direction of force on the figure above. Okay, so let's try the top. UV cross E. We see the hiccup here. So this is why this question was asked, because there's actually no force on the top of the loop. Because if I try to QV cross B it, I have a parallel / anti-parallel B field. So no force. Bottom will be the same because it's still parallel. You just flip whether it's parallel or anti-parallel, doesn't make it. All right, top and bottom though. Let's do, the left and right. Let's do the left first. So left, I would do QV, current goes down, cross B, my palm points at me. So that's going to be out of the page. And what is that? That's just BIL. BIS. And we'll check it. It should, since I just reversed the current by symmetry, it should go into the page. Let's check QV, cross B, my palm does point at you. So that's going to be BIS into. So the top and bottom forces are equal to 0 because we have current is parallel B field. And then F on the left side is equal to F on the right side, which is equal to BIL. And that's that. All right, net force. Well, net force, 0, 0, BIS out, BIS in. those cancel. So even though we got into and out of the page forces, they're still canceling forces. But here's the interesting part. Net rotational motion. So let's try that. Well, I'm not pressing on the top or bottom, so that doesn't matter. So now let's think about what's going to happen if I have a square. So I'm looking at the left side here. So first, if I push on the square, that would tend to make this left side sort of get lifted out of the page. So this side of the loop is going to swing sort of this way. And then BIS, then if I push my loop into the page, that's going to cause it to swing this way also. So we actually are going to get a rotation. This loop is going to start swinging this way. So we are actually going to get a rotation. The loop will begin to rotate about its center, about an axis perpendicular to the magnetic field. So just to sort of draw what's going to happen here, we have our loop. And we're pushing sort of like that. So what's going to happen is if I draw myself an axis, I was going to say axes, an axis like this, it's actually going to rotate sort of like that. So we will actually get a rotation here with this end is going to pop out of the page initially, this end is going to pop in. So we'll see if you put a loop in a uniform B field, you actually aren't going to ever get a net force due to symmetry, but you can get a net torque, meaning you can get rotation. Now, Physics C might not even ask this. Like, do we have to understand this sort of, you're not going to be asked about the rotation direction, but you could actually be asked, will it rotate or not, based on this info. Especially not throwing in things like moment of inertia or things that you've repressed from mechanics. This, however, is the most important thing we will do in this section. It's talking about forces that wires exert on each other. So why is that even something that's going to happen if they're uncharged? Well, these wires will exert magnetic forces on each other. Why is that? Well, last section we said that wires make magnetic fields. So this wire, if I pull out my thumb in the direction of current, above the wire, it's popping out of the page, and below the wire, it's in. So actually, the top wire would exert a magnetic field, or generate a magnetic field pointing into the screen at the location of the bottom wire. So what that means is that this bottom wire is placed in a magnetic field. And what is a wire? Well, a wire is a set of charge carriers. So each wire generates a magnetic field at the other. And since the other wire is carrying current, we have charge carriers placed in a perpendicular magnetic field, so we will get a force. So let's do that. So first, let's get the magnitude. So it's BIL. And both currents are I, so I didn't make a distinction. So we weren't given B, but we actually know what B is. We said in the last section, the B field from a long wire is mu naught I over 2 pi r, but r in this case is the wire separation D. We get that. I is I, and L is L. So FB is going to be equal to, we just collect an extra I on top, so we get mu naught I squared L over 2 pi D. And now let's get the direction. So we have our current going to the right. So QV, and I'm doing the bottom wire, by the way. So QV cross B, the B field points into the screen. So my palm slaps the charges up in that wire. So actually, these wires that are carrying the same current, we get an attractive force acting on that wire. So it would be up. And that's actually opposite of the charge rules, because Coulomb's law, like charges, repel each other. But like currents actually are attracting each other. So before we talk about that, what's the net force? Oh, this is the magnetic field. We did both of these things. we said earlier that B was just going to be mu naught I over 2 pi d into the page. That what is the magnitude and direction of the force on the top wire by the bottom? So notice, what are we asking? We're asking F, and I'm writing this out just to really prove a point here. F on top by bottom is equal to, well, we just found F on bottom by top. This is just totally our like word soup that indicates Newton's third law is at play. This is Newton's third. So the forces are going to be equal but opposite by Newton's third law. So force on the top wire by the bottom is equal to the force on the bottom by the top, except opposite direction. So we would get a downward force on the top wire because they have to be equal yet opposite. I know some people don't like that language. I'm fine with it. So this is going to be mu naught I squared L over 2 pi d down. So notice these create a Newton's third law force pair. We have mu naught I squared L over 2 pi d up and mu naught I squared L over 2 pi d on the other object in the opposite direction. So this is a fact. This is a pretty well-known result. This is almost like a magnetic Coulomb's law with some major differences, where we have our BIL force turns into mu naught times the product of the two currents times the length of the wires divided by their separation distance to the first power, not the second, because our long wires are 1 over r for the field, not 1 over r squared. Often, though, if the wires are infinitely long, we'd get infinitely large forces. So we'll look at sort of the force per unit length, and that just divides out a length. So it makes the formula a lot cleaner, where it looks more Coulomb-esque. And a fact about this is that you could do the right-hand rule every time, but instead you could just remember that like wires attract. So it's actually opposites. So this would be our relationship here. So actually like currents attract, opposite currents repel, which is totally the opposite of how charges work. So the magnetic force behaves oppositely. Prove it. So this is not too hard to prove because we've essentially done this in the previous question where we're going to have two wires. And we'll separate them by a distance d. So we can say, actually, I think it was r. It was r in the. So we'll say that F on 2 by 1 is going to be equal to the magnetic field from 1 times I of the second wire times the length of the second wire. So lots of subscripts to manage here. So what is the B field for wire 1? Well, it's just mu naught I over 2 pi r for wire 1. Then we have I2, and the length is just L. So this means FB equal to that. So we can divide both sides by L and get the force per unit length, magnetic force per unit length on a wire is equal to mu naught over 2 pi constant times the product of the two currents divided by their separation distance. As expected, we have proven our result. All right, now let's drive an expression for the force per unit length on the leftmost wire in this setup below, assuming the wires are very long and carry parallel currents like this. So these are wires either carrying current into the screen or out. they're very long, which allows us to just look at this force per unit length. So we're going to say that lowercase f, as you'll see it sometimes, is equal to the magnetic force per unit length. So we want the leftmost wire. So first of all, we see that the 2I wire is carrying an opposite current, and opposites repel for this magnetic force. It is not the same as Coulomb force. So this would be F from the 2I, force per unit length. And then 4I, this is a parallel current. It attracts. So let's work it out. So our net force per unit length is of course going to be the net force per unit length from the 2I plus the net force per unit length from the 4I. From the 2I, of course, our new formula is force per unit length equals mu naught I over 2 pi r. Mu naught I over 2 pi r. So we get mu naught times the first current times the second current divided by 2 pi. And this separation is just 1d between the first two. And what force is this? This was to the left. And then similarly, we get mu naught. First current is still I, but this time we're looking at the 4I. And it's 2 pi again, but now the distance is d. D makes 2d. This is to the right. All right, now something interesting happens. So we'd get goodbye. The 2's go away, so we get mu naught I squared over pi d left plus mu naught. 2 and 2 make 4, but 4 cancels this 4, so I also get mu naught I squared pi d, but this time it's to the right. What does that mean? Well, we have force per length left, force per length right. They're the same force per length, so it's actually 0. And there was a way we could have actually seen that without doing the problem, because the currents are opposites. So we know that they're going to exert forces that are in opposite directions. One current is twice as big, but it's also twice as far away. So that wouldn't be 0 if it was an electric force, 1 over r squared, but it is 0 in this case because it's actually just linear on the denominator. So we doubled the distance and doubled the current. Those effects exactly canceled each other. So forces cancel. And if the force cancels at every length, the net force. All right, now for a classic. This is a classic lab on magnetic force where we put some sort of force probe on some current carriers, and we want to actually find something about it. A group of students are investigating the magnetic force between two long parallel wires. Their length is given. So we're separating them. We can assume that these wires can be modeled by the long formula if this long length is much greater than their separation. So in this case, the length is 5 meters, and we're separating them by not even a quarter meter. So, of course, what do we want? We want the current in each wire. I have no idea why they're not using an ammeter, but as with a lot of these lab questions, they're contrived to make you best fit for something. It's usually mu naught. Usually mu naught is the value defined here, but I kind of got sick of just making it solve for mu naught because mu naught is disgusting and has disgusting units. All right, so what is that? Well, we know that FB between two wires is mu naught times I1 times I2 divided by 2 pi r, and we have to include our length. So what is known in this experiment? We don't know our current, but it is the same. We know length, and we're varying this distance. Of course, we know mu. So we can say that FB for this experiment is equal to mu naught over 2 pi times I squared L divided by R. So our variables are I squared L, and R. We do know L, so I can move that. Now we don't know I, but it is a constant, so we can also lump that in. So we can get FB is equal to mu naught L times I squared divided by 2 pi times 1 over R. So this actually tells us how to linearize, because we now have a formula that says the magnetic force between the two wires is mu naught times L times I squared divided by 2 pi times 1 over R. So we can shove magnetic force into its box, and we can shove 1 over R into its box. So we can graph FB versus 1 over R. And then everything else is going to be our slope. This is going to be kind of a nasty slope to deal with. Now, if you're someone who likes to graph everything in your other box, that's might actually be preferable here. It's just going to be really annoying with the units. So you can actually put FB versus mu naught L divided by 2 pi over R in that box, and your slope would be I squared. So you just square root slope. So this is going to be a bit annoying, but we'll manipulate it. All right, blah, 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 off-camera mining. Axes are scaled with units. It's a linear scale. 1 over D has correct units. FB has correct units. Best fit line, Desmos. All right, so we said that the slope of our best fit line was equal to mu naught L times I squared over 2 pi. Right, because that is the constant in front of the 1 over R. And the thing we wanted was I. We can get 2 pi times slope is equal to mu naught Li squared. So 2 pi times slope divided by mu naught L is equal to I squared. So this means I squared is equal, this means that I, regular I, is equal to the square root of 2 pi times the slope divided by mu naught L. And I'll save you the trouble and say this is approximately 8.1 amps from my computation. So that's quite a lot of current. Yeah, so that's kind of a tricky lab manipulation question. And why is it going to be about an amp or on the order of single or double digit amps? Well, let's see. Mu naught is about 10 to the 6. And the slope was about 10 to the minus 5. Yeah, it makes sense, right? Because we're going to get about 10 to the 6 here. So orders of magnitude work out. So I'm not totally surprised there. All right, now some force balancing. So we have our magical current carrying wires from before are carrying current. They're separated by some distance, and the top wire is suspended by a string. And this bottom wire is initially on the ground, but we've found some separation such that this bottom wire actually starts to levitate off the ground a bit. So what is happening here? Well, these wires have the same mass, lowercase m. So both wires are going to feel some sort of gravitational force down. Maybe I'll give that 2 ticks. You know what? I don't like substituting. We're going to call this FG. I'm leaving space here because there could be multiple. Alrighty, so everybody has a gravitational force. So you would have some sort of mg, and you would also have some sort of mg. Okay, but this is about magnetic forces, and like currents attract. So there's actually going to be a magnetic field causing an attractive force there, and a magnetic force causing an attractive force there. All right. Now, if this wire is on the ground, it would have some sort of normal force from the ground up, but it doesn't. So actually, we're done with the bottom wire. The bottom wire the bottom wire is going to have an attractive magnetic force. And if it's being levitated off the ground, there's no normal force, so the magnetic force exactly balances the gravitational force. So we actually can write the relationship, the Newton's first law relationship, that the magnetic force and the gravitational force are going to balance each other. And because of Newton's third law, we actually know that the magnetic force is going to be equal yet opposite on the other wire. So I'm giving it the exact number of ticks now. So we see here that this totally cancels, and this we have 4 ticks down. And as per usual, tension comes last. This is like your balancing agent, same idea like as normal force here. So this means your Ft has to balance the combined efforts of both forces. So Ft would be 1, 2, 3, 4 clicks up. 1, 2, 3, 4. So if I wrote a Newton's first law equation here, this would say that the tension force must balance the combined efforts of the gravitational and magnetic forces, because those are both pulling the wire down. All right. So let's do some expressions now. What distance allows levitation to occur? Well, if levitation is occurring, that means that the forces are balanced on this bottom wire. So it means that on the bottom wire, the magnetic force and the gravitational force are equal to each other. We do have an expression for the magnetic force between 2 wires. It's the same one from the lab question. It's mu naught IIL divided by 2 pi times the separation, which is y in this problem. And mg is our gravitational force as per usual. So if you multiply both sides by y, you'd get mu naught I squared L over 2 pi equals mgy. So we'd get y, the distance that causes separation to occur, or levitation rather, is mu naught I squared L over 2 pi mg. Gross. What is the tension in the top string while the bottom wire is levitating? Well, now we use our other force relationship that says the tension must balance both the magnetic force and the gravitational force. And actually, we know from the previous part that FB is actually equal to FG, because the levitation is occurring. So this magnetic force totally balances the weight of the cord. So this actually means that Ft is simply equal to 2 mg's. We can actually see that from our force diagram, because from our force diagram, we see that the gravitational force had to be the same as the magnetic force, because over here, they balanced. So the tension force was really just pulling up with 2 weights worth. Now, I didn't explicitly say you couldn't use y. So if you put y in this expression, you would get, you could also have written something like the tension force equals mu naught I squared L over 2 pi y plus mg. But if you substitute what y was, you will get 2 mg, because y is going to be in the denominator. So you see like a huge reciprocal happens. The 2 pi cancels, the L cancels, the mu naught cancels, the I squared cancels, and the mg just swings up to the top, giving you an extra mg as expected. What if instead of giving mass, because we're saying we have a really long wire, what if instead of mass, we gave the mass per unit length? How would that determine our y? Well, we can actually just do the same sort of thing. So we actually solved for y. Y was equal to mu naught I squared L over 2 pi mg. So if instead of giving m, we were given this concept of lambda, which as per usual, it's a length density. So lambda was defined as mass per unit length. So that means our mass could just be written as mass per unit length lambda times the length L. So all we got to do is substitute M is actually just lambda times L, just like Q is lambda L for a length charge. So this tells us that Y is equal to mu naught I squared, and that's it, because actually the L cancels. Divided by 2 pi lambda. So this should actually make sense that the length cancels, because if you're given the mass per unit length, you get sort of a gravitational force per unit length, and that exactly needs to be canceled by the magnetic force per unit length, which takes the L out as well. And it should make sense that if you have more current, you're able to separate the wires by more before attraction occurs. And it makes sense that if you have more mass density, that's a larger gravitational force. So you have to get the wires closer to balance this larger mass per unit length. Almost there. All right, this one's tricky. So this is a good problem, but it's a hard one. So now, instead of just a single wire placed near another wire, we have a loop with length. So this is combining multiple things we've done before. So the currents are still I, and this one is counterclockwise. And we're going to want to find the net force on the loop, magnitude, and direction. So direction is always easier because we can just right hand rule it. Or you don't actually have to, because we know that we know like currents attract, but we'll need it for the other side. So using my right hand rule here, this is my current that's going up. So if my current goes up, my fingers pop actually out of the page when I'm to the left of the wire and into the page when they're to the right of the wire. So those are the field directions from this wire. So everybody is going to experience an into the page B field over here. So we'll do that going counterclockwise starting there. So QV cross B, left. And actually, we'll have to look at their values in a minute here. So we'll just start it out like this, and then we'll adjust. QV cross B, down. QV cross B, right. QV cross B, up. Symmetry. All right, so how should these actually compare? So yes, in the other problems, the force is entirely canceled, but that's because we had a uniform magnetic field. The magnetic field from a wire is not uniform. We said that B is equal to mu naught I for 2 pi r. So as you get farther from the wire, the B field decreases. So what we really should have is something that looks like this, or maybe there's a large X when I'm close to the wire, then there's a medium X when I'm farther away, and it gets smaller, smaller. So this wire is exerting less force on parts of the loop that are farther away. So what I should do is we actually know that the leftward force, this is the close side, going to be the largest. Then the force on the far side will be the smallest. And then you'll get sort of like a medium, you'll get a medium equal and opposite cancellation top and bottom. So what's the direction? It's going to be to the right, because that is the larger force. And we also could have done a shortcut of like currents attracting and opposite currents repelling. So these are opposite currents, so we get a repulsion, and these are like currents, so this is an attraction. But the repulsion is going to be larger because the opposite wires are closer together than the attractive wires. So what is the magnitude of that force? Well, we know the magnitude of FB is going to be FB on the left side minus FB on the right side. because the left side wins, so I'm just going to write it like this. The net force is going to be this repulsion minus this attraction. So it's going to be BIL minus BIL. B on the left side is mu naught I over 2 pi. Where is that? Well, this is just d. The left side of the loop is just a distance dUA. And then this is why the forces don't cancel, because the field is not the same. Because it's not dUA, the other side of the loop is d plus the entire square side length s away. D plus s goes there. And now we can factor out. A lot of things here, actually. And I think I have to shrink this so we can space here. So we'd get mu naught I squared L over 2 pi. And then we'd get 1 over d minus 1 over d plus s. That is our answer. So notice this will be a positive constant because we have, we're subtracting a fraction with a larger denominator. So this is a smaller number. Yeah, that's a tricky one. This is a really good question though, because it incorporates multiple sections. So the force is that magnitude and it points. All right. There are current carrying wires and the forces experienced on them.